So you are welcome. We're looking at the refraction of light. So in our previous video, we've talked of the reflection of light, how light reflects on plane mirrors and curved mirrors, and how their images are formed after the reflection. So we are looking at onto the next one, the refraction of light. How light is refracted when it's moving from one medium to another, the images formed, the characteristics of the images, and some conceptual understanding explanations that we can get out of the refraction of light. So, refraction of light is the bending of light as it passes from one medium to another, caused by the velocity of the light. So, when light is moving from one medium to another, the light ray tends to bend as it enters the new medium, and this is due to the change in velocity of the light entering the new medium. So that is termed as refraction. So the light changes in speed and direction as it's moving from one medium to another. And this scenario on this concept is termed as the refraction of light. So this phenomenon occurs as the interface between two media, which leads to a change in the direction of the light ray. So as I said earlier, when the light is moving from one medium to another, the direction changes since it is moving from one medium to another, and this is due to the change in the speed of the light. So the various optical effects such as formation of lenses, magnifying glasses, and rainbows are due to the refraction of light. So this refraction of light can lead to some various optical effects and phenomena, real life experiences that we have and that we see around. And this is due to refraction of light. So if you look at this diagram, then we take this part of the diagram to be our air for the first medium where the light is coming from. So our incident light ray coming from air hits this boundary at a certain angle, which is the angle of incidence. When it hits the boundary entering the new medium, the light ray tends to bend a little. There's a change in direction of the light ray due to the change in speed of the light in this medium. And this speed change is due to the refractive index of the medium. So that is totally some basic explanation from refraction of light. So when light travels from one medium to another, its velocity and wavelength change, but the frequency remains constant. So when light is moving from one medium to another, there's no change in frequency, but the velocity and the wavelength is altered. So we take note of that. The ratio of the speed of light in vacuum to the speed in a given material is termed as the refractive index of the material. So that is refractive index, which is denoted by N, is equal to the speed of light in vacuum over the speed of light in a given material. So we can then use these given parameters to find the refractive index at which the light is moving into the material at which the light is moving into. We can use the speed of light in vacuum and the speed of the light in that particular material to find the refractive index of the material. So if you look at this diagram, the first part is the light ray is moving from a less dense medium, considering air to be for medium 1. It's moving from the less dense medium, hits this boundary and enters a denser medium. So the light tends to bend a little bit closer to the normal. So there's angle of incidence and there's angle of refraction. And there's a little bit of reflection. And we can use the speed of the light in the vacuum and the speed of light in water to find the refractive index of this medium, to find the refractive index of water. So this is basically the explanation I can give of the equation. You can use the speed of light in vacuum and the speed of light in water to find the refractive index of water. And we should take note that the refractive index of water is greater than that of air. The refractive index of water is greater than that of air. So the Snell's law, also called the law of refraction, gives the relationship between angles and indices of refraction. The Snell's law gives a relationship between the angle of incidence, angle of refraction, and the refractive index of the media in context. So the law states that the ratio of the sine of the angle of incidence to the sine of angle of refraction equals the refractive index. So if you take a fraction of the sine of the angle of incidence to that of the sine of angle of refraction, you can equate it to the refractive index. And this refractive index too can be fracted to the refractive index of the first media over the refractive index of the second media. So we can therefore generate a relation for the angles and the refractive index. So this implies N1, which is the refractive index of the first media, times sine theta 1, which is the angle of incidence, is equal to N2, which is the refractive index of the second media, times sine of theta 2, which is the angle of refraction. So we can use this relation to find specific refractive index of specific media in context. So if, let's say, the light is moving from glass to water, we can use this relation, either we don't know the refractive index of the glass, to find the refractive index then of the glass. Now, some real-world examples of refraction of light are the apparent bending of a stick partly immersed in water. So the submerged part seems closer to the surface than it is actually. So the submerged part seems to be very close to the surface. So if you look at this diagram, this is the actual length of the object immersed in the water. When an observer observes it, he or she sees the object to be closer to the surface than the actual depth. So this example is due to the refraction of light. So when the observer looks through the water, the object in the water sees the object closer to the surface than the actual depth of the object. So this is due to refraction of light. And also light from the sky approaches hot roadways at a gazing angle and refracts upwards so as to miss the roadway and enter a driver's eye, giving the illusion of a pool of water on a distant roadway. This example is what we know as mirage. So at a distant hot roadway, you can see a pool of water in the middle of the road, thinking there's some pool of water there, but it is actually an illusion due to refraction of light, which has caused to refract the rays hitting the road into the driver's eye, seeing a pool. Now we can talk of the real and apparent depth. So the real depth is the actual depth of an object from a surface, while the apparent depth is the perceived depth of the object when viewed from a denser medium. So let's say we've dipped an object into a beaker of water, and we know the actual depth of the object when we placed it into the water, but when we view the object at a certain angle, we can see that the object is appearing a little bit closer than we thought it would be to the surface. So that's the distance that we perceived to see is the apparent depth, and the actual depth of the object is the real depth, and there's a relation between them. So if you look at this diagram, the fisherman sees the fish to be closer to the surface of the water than the actual depth of the fish. This distance of the fish to the surface is the apparent depth, and this distance, which is the actual depth at which the fish is, the actual depth is the actual depth. So there's a relation between these, and some calculations and dashings can be made out of it. So the depth of the image is less than the depth of the object. The depth of the image is less than the depth of the object. So if you look at the object which has its actual depth, its distance is greater than the distance of the image that the fisherman is seeing. So we can therefore determine the apparent depth since it is related to the real depth and the refractive index of the medium. So there's a relation between the real depth, refractive index, and the apparent depth. And this equation is sine theta 1 over sine theta 2 is equal to n1 over n2. And this is also equal to the apparent depth over the real depth. The apparent depth over the real depth. So we can therefore determine the apparent depth of the object if we know the refractive index of the two media and the actual depth of the object.